Welcome to this lecture. This lecture is a continuation of earlier lecture. So, in the earlier lecture, we have proved that, or we found that J plus minus alpha beta is equal to C alpha beta plus minus alpha beta plus minus 1, and let me call it as equation number 18. Right. So, since we know that J square is equal to Jx square, Jy square, Jz square, and this is always greater than or equal to 0 because this is always a positive quantity. So from here I will arrive at conclusion that J square minus Jz square is equal to Jx square plus Jy square, and this is again greater than or equal to 0. Now I consider alpha beta J squared minus Jz square alpha beta. It can be written as alpha beta, and the eigenvalue of J square is basically h cross square alpha, and for Jz it is h cross beta. So if I put these values, then this equation will become h cross square alpha minus h cross beta its square into alpha beta, and it can be taken outside. So if I take it outside, so it is h cross square alpha minus h cross square beta square. Right, so it can be written in this way. It is alpha beta and it is alpha beta. Now what I can do, I can write down it as h cross square alpha minus beta square and alpha beta and alpha beta, and this is the normalization condition and its value will be 1. So that means I can say that it is h cross square alpha minus beta square, and it is always greater than or equal to 1. So from here I'm arriving at conclusion that alpha is greater than or equal to beta square. This inequality leads to this particular relation. Now since beta has an upper limit, and let me call that upper limit as beta max. So if it is the maximum value of the beta, that means there must exist a state alpha comma beta max which cannot be raised further. So if it is so, that means if I operate this alpha beta with the raising operator, then its value will be equal to 0 and beta has reached its maximum value, right? So now operating both sides with lowering operator. So if I operate both sides with the lowering operator, then it will become alpha comma beta max and it must be equal to 0. And let me substitute its value as I know from equation 11. of our lecture, that j minus j plus is equal to j square minus jz square minus h cross jz. So if I do this here, then it will become this j square minus jz square minus h cross jz, and it is alpha plus beta max and is equal to 0. As I know the eigenvalues of j square and jz square, so if I put those eigenvalues here, it is h square alpha minus h cross beta max whole square minus h cross beta max, and it is alpha comma beta max and is equal to 0. So I can take it outside as cross square, and here it will be alpha beta max square minus beta max, and it is alpha plus beta max, right, and is equal to 0. So from here I can say that alpha minus beta max square minus beta max is equal to 0, and that means this alpha is equal to beta max square minus beta max, which implies that alpha is equal to beta max into beta max plus 1. Sorry, if I am bringing this towards that side, okay, it will become plus, so it is also plus. So this is one equation which I am getting, and let me call it as equation number 19. And in the similar fashion, after n successive applications of lowering operator on alpha beta max, that means over this state factor alpha comma beta max, if I apply or operate with j minus or the lowering operator n times successively, then this reaches its lowest value, and further then we cannot reduce the value of beta minimum. So that means we are arrived at a point alpha beta minima such that if I operate further with this lowering operator, this alpha comma beta minima, then it cannot be lowered further. So that means its value must be equal to 0. Now operating again both sides with j plus. So if I operate with the j plus and j minus, then it is alpha comma beta minima, it must be equal to 0, and let me put their values, as I know from earlier lectures that this j plus j minus is equal to j square minus jz square plus h cross jz, and this is basically equation number 10 of earlier lecture. So if I do this, then I can write down it as it is j square minus jz square plus h cross jz, and alpha beta minima, it must be equal to 0. If I substitute their values as I did in case of earlier, so it is h cross square alpha minus beta minimum square plus beta minima, and it must be equal to 0. So from here I can write down it as alpha is equal to beta minimum square minus beta minimum, and I can write down it as beta minimum into beta minimum minus 1, right? So if I do this, then it will, let me write down it as equation number 20. So if I sum up these two equations, then I can write down that alpha is equal to beta max plus 1, and alpha is equal to beta minimum plus 1, sorry, not plus 1, but it's a minus 1, and this is equation number 19, and this is equation number 20, and this is possible if beta maximum is equal to negative of beta minimum. Let me verify it. So let us consider alpha is equal to beta maximum plus 1. So in place of beta maximum, let me put it as beta minimum minus, right? So if I multiply this negative inside it, then it will become beta minimum into beta minimum minus 1, right? So that means this is equal to this one. So this is possible if and only if beta max is equal to minus beta minimum, right? So up to this, we found that beta minimum was obtained by n applications of successive n application of J minus on alpha beta max. Therefore, beta max can be written as beta minimum plus n, but beta max is equal to negative of beta max. I substituted its value plus n, and this is beta max plus beta max is equal to n. So twice of beta max is equal to n. So that means beta max is equal to n by 2. And let me call it as equation number 21. And from here I can conclude that beta max can be integer or half odd integer depending on n is odd or even. Sorry, even or odd, not odd or even, but even or odd. Now let me introduce J for beta max. So therefore J is equal to beta max, and it is equal to n by 2, and let me call m is equal to beta. As eigenvalue of J square is given by h cross square alpha, and alpha is equal to beta max into beta max plus 1, and it is j into j plus 1, and let me call it as equation number 23. Also, beta lies between beta max and beta minimum. So therefore, beta minimum is less than equal to m is less than equal to beta max, and beta max, the value will be j, m will remain as it is, and beta minimum is nothing but it is the negative of this, so that's why it is minus j will be there. And let me call it as equation number 23.1. Now j square is equal to h cross square alpha. This is the eigenvalue of it, and the value of alpha, as I know from equation number 23, that it is j into j plus 1, and similarly jz can be written as h cross beta is equal to h cross m. Therefore we can write that j square when operates over jm, it's equal to h cross square j into j plus 1, it is jm, and jz, jm, it can be written as h cross m into jm. Let me call it as equation number 24. Here the possible values of m are minus j minus 1, comma, and so on, j minus 1 up to j, and that means for each j there are 2j plus 1 values of m. So let us understand it by taking an example. So for j is equal to 1, the possible values of m are minus 1, 0 and 1, and similarly for j is equal to 5 by 2, I can write down it as minus 5 by 2, minus 3 by 2, minus 1 by 2, 1 by 2, 3 by 2 and 5 by 2. So similarly I can write down the values. Also another thing which we have to keep in mind, that j and m are orthonormal. And what does that mean? That means that j prime, m prime, jm is equal to delta j prime j and delta m prime m. So this is orthonormality condition which we have to keep in mind. Let me call it as equation number 25. Now let us now determine eigenvalues of j plus minus with jm. So now consider equation. This is j plus minus alpha beta. It can be written as c plus minus alpha beta, alpha comma beta plus minus 1, right? So as we know, so using this equation we can write down it as jm is equal to cjm plus minus, it is jm plus minus 1. Let me call it as equation number 26. So using this we can write down, we can taking only one term, then it can be written as Jm is equal to Cjm plus Jm plus 1, right? So now using this equation, I can take its dagger, and if I use this, then this can be written as this way. Then it is Cjm plus its mod square, then it is Jm plus 1, and it is Jm plus 1. And this is nothing but using normalization, this is equal to 1. So if it is so, I can write down this as this is Jm, J minus, it will become J minus, and it will become J plus, and it is J, this one, Jm, and it is equal to Cjm plus mod square. So that means using this, I can write down as Cjm plus is equal to, it's the square root of this quantity, it is Jm, J minus J plus Jm whole under the root, and let me substitute its value. So if I substitute its value, this can be written as, this is h cross square alpha minus h cross square beta square minus h cross beta, and it is Jm and whole under the root, and this h cross square can be taken outside, so it is h cross and is alpha minus beta square minus beta, it is Jm and whole under the root, and its value is 1. So if I do this, then this can be written as this Cjm plus is equal to h cross j into, because the value of alpha will be j into j plus 1, and here it is m square minus m, so m square minus m under the root. So it can be written as h cross j into j plus 1 minus m into m plus 1 whole under the root, and let me call this as equation number 27. Similarly, we can write that Cjm minus is equal to h cross j into j plus 1 minus m into m minus 1 whole under the root, and let me call it as equation number 28. Therefore, using equation 26, we can write j plus jm is equal to cj plus j into m plus 1. So it is h cross j into j plus 1 minus m into m plus 1 whole under the root j into m plus 1, and say it is equation number 29. And this j minus jm, it can be written as cj minus j into m minus 1. So it can be written as h cross j into j plus 1 minus m into m minus 1 whole under the root j into m minus 1. And let me call it as equation number 1. And these two equations can also be remodified. So to modify these, consider as j into j plus 1 minus m into m plus 1. It can be written as j square plus j minus m square minus m. So j square minus m square plus j minus m, and this j minus m can be taken outside, so it can be written as j minus m j plus 1. So here it is j plus m as it is, and here it is plus, right? So if I use this in equation number 29, then equation 29 using this will become that this j plus jm, it can be written as h cross j into j plus 1 minus m into m plus 1 under the root into j into m plus 1, and which is further equal to h cross j minus m and j plus m plus 1 whole under the root into j into m plus 1. And let me call it as equation number 31. And similarly, equation 30 can be written as, similarly, equation 30 can be written as, let me write it down as j minus, okay, it's a j minus jm is equal to h cross j into j plus 1 minus m into m minus 1 under the root j into m minus 1, and which is further equal to h cross j plus 1 j minus m plus 1 under the root over j into m minus 1. And let me call it as equation number 32. So let us now calculate values of this jx, jm and jy, jm. So to calculate these values, let me consider this. So to consider this, let me write down it as jx, jm, it is equal to 1 by 2 j plus plus j minus, this is the standard value of this jx, and it is jm. So it's equal to 1 by 2 j plus jm plus j minus jm, and this can be taken outside. It's 1 by 2, this is the common. So if I put their values j plus and the j minus here, then it can be written as h cross by 2, it is j minus m, j plus m plus 1, j m plus 1, it's under the root, and plus j plus m and j minus m plus 1 under the root, it is jm minus 1, and right. And similarly, I can write down values for this jy. So to do that, let us proceed as follows. Jy jm is equal to 1 by 2 iota j plus j minus, and it is jm. So as we proceed here, in the similar fashion, I can write down it as h cross over 2 iota j minus m, j plus m plus 1, it's under the root into j m plus 1 plus j plus 1, not plus but minus will be there, minus j plus m, it is j minus m plus 1 whole under the root, it is j m minus 1, right. So let me call it as equation number 33 and this as equation number 34. This is the way that we have calculated the values of jx and the jy. Now let me calculate their expectation values. So that means now I am interested to calculate its expectation value, right? So to calculate expectation value of jx, let us proceed as follows. So let me put their values. So it is jm, it is h cross by 2 j minus m, j plus m plus 1 whole under the root into j m plus 1 plus j plus m, j minus m plus 1 whole under the root, and it is j m plus 1, sorry, not m plus 1, it is j minus 1, and h cross by 2 is a common for all, so it can be written here. It doesn't matter where I have to, okay, so not like this, but let me do one thing. I'm a little bit wrong. Yeah. So it is h cross upon 2. It is h cross by 2. It is j minus m and j plus m plus 1, and it is j into m plus 1 plus h cross by 2 j plus m, j minus m plus 1, it's under the root, and j into m minus 1, right? So this, after simplification, this can be written as, this is h cross by 2 j minus m, j plus m plus 1, it's under the root, it is jm and jm plus 1 plus h cross by 2, it is j plus m and j minus m plus 1 whole under the root, and it is jm minus 1, and its value will be 0 and its value will also be 0. So this overall makes it is equal to 0. Thus we conclude that this expectation value of jx will be 0, and similarly I can say that expectation value will be jy will also be 0. That's what we can prove. Now we have to find out the expectation values of jx square and the jy square, and they comes out to be equal. Means next is expectation value of jx square and jy square, and we have to prove that they comes out to be equal to 0. Comes out to be equal, and they have some definite value. So let us proceed as follows. So yeah, it is jx square, as we know that it can be written as 1 by 4 j plus square plus j plus j minus plus j minus j plus and j minus its square. This is equation number 5, and similarly we know that jy square is equal to minus 1 by 4 j plus square minus j plus j minus j minus j plus j minus its square. Now to find out the it is from equation number 6. Now consider expectation value of this. So it means it is the expectation value of j plus square, j plus j minus j minus j plus j minus its square. Okay, I missed the operator form, so I will put hat on every term. That's what I'm getting, and this can be further written as j plus its expectation value plus j minus j minus j plus j minus, but expectation value of this is also equal to 0. This is equal to 0. This is a standard result. So it can be written as j plus j minus j minus j plus its expectation value. Let me call it as equation number 35. And similarly, we can find out the expectation value of jy square. It is minus 1 over 4 j plus square minus j plus j minus j minus j plus j minus its square, and its expectation value will be 0. Its expectation value will be 0. So it is minus 1 over 4 minus j plus j minus j minus j plus its expectation value, and minus can be taken outside. So if I take it outside, so it is j plus j minus j minus j plus. This is equation number 36. So these two equations ensures that expectation value of jx square is equal to jy square. Now let us try to find out their values, that what should be their value. So as I know that jx square is equal, j square minus jz square is equal to jx square plus jy square. So that means jx square, its expectation value, jy square, its expectation value is equal to j square minus jz. It's their expectation value, but both are equal. So that means jx square is equal to jy square, and it can be written as 1 by 2 j square minus jz square. What are the values of this? The expectation value of it is equal to h cross square into j plus 1, and 1 by 2 will be here, plus h cross m h square, sorry, minus will be there, it is its value, so it is h cross square by 2, it is h cross square by 2, and yeah, it is j into j plus 1 minus m square. That means jx square is equal to jy square, and it is equal to this one, right? So this way we have calculated their expectation value, right? So with this lecture is finished, and thanks for watching this lecture.